So welcome back, friends. So we did a slight detour in the last class where we looked at uh, uh, the Dirac sea and the equations of the and its physical consequences. So the Dirac sea uh, uh, essentially was proposed to avoid the catastrophe associated with atomic states collapse, essentially in the presence of negative energy states, energy solutions and the Pauli exclusion principle. So what Dirac proposed was that the idea that the using Pauli's exclusion plus Pauli's exclusion principle, that you can avoid this catastrophe by introducing something called the Dirac sea, where all the states are completely filled up. Essentially all the states, all the negative energy states are completely filled up. Now along the way he introduced the concept of positron, because he introduced that the absence of electron is also called a hole, and the hole is nothing but a positron, as we presently call that as a positron wave function. Hole is nothing but a positron state, as we have seen, essentially that because of the absence of any particle in the vacuum can be treated as a creation of a particle. Okay, can be created as a thought of as a creation of a particle in the with positive energy. So this can be seen essentially, and we argued for the charge, electric charge, and similar statements can be made for the electric mass, charge and mass, and you can also actually do perturbation theory with this with the Dirac theory, okay, with an electromagnetic radiation essentially. And then we looked at consequences. One of the main consequences we looked at due to the presence of the Dirac C is so called the electric charge renormalization, and like I said, okay, the electric charge increases in its strength. Essentially the electric charge increases in strength as we probe closer and closer, and we can actually derive how it in full quantum field theory we can actually derive how this is actually changes with energy or with respect to the distance. And I have shown you some numbers essentially that at say at atomic scales at around Armstrong units, essentially the electric charge is given by the fine structure constant, which is 1 by 137, and so the electric charge measured will be something like this, essentially 4 pi times root of 137 square root of 4 pi by 137. But as you move closer, as you start measuring the electric charge at distances smaller than nuclear distances, essentially around 1 Fermi or so, at those energies and even smaller, so at those energies the mass the electric charge is essentially, instead of 1 by 137 it becomes 1 by 127, and so it increases essentially. So the electric charge increases. It increases logarithmically with respect to distance and with respect to, now the same thing plot can be plot with respect to energy. Okay, with distance it looks like this, with energy it looks, as the energy increases it looks the reverse way, essentially it increases logarithmically. At some energy it blows up, and the energy which becomes in infinity is called at some point when the charge becomes infinity is also called the Landau pole. So this is a theoretically driven graph, but experimentally we have seen this thing at least 2-3 different energies, essentially at 3 electric charge has been seen, and it actually follows the theoretical prediction. There are experiments which measure these things essentially at very low energies, and okay, like quantum Hall effects and so on, so and all the way up to colliders, essentially at colliders which are at yeah at multi TeV range. So this is about electric charge. So now let us come back to other solutions of Dirac equation. We will come back to this Dirac and its interpretations when we start looking at other aspects of Dirac theory, especially in the presence of an electromagnetic system. Okay, other solutions of Dirac equation. One of the most important solutions of the Dirac equation is the massless limit of the Dirac equation. Now if you remember, the Dirac equation is I del slash minus m psi is equal to 0. Now but this is a matrix equation, you should remember how to write it down. Essentially it is completely different. Essentially I remember it is, you can write it in terms of alpha dot p plus beta dot m times psi is equal to 0 essentially, and it's not in terms of gamma matrices, essentially instead of, if you write it in terms of beta matrices and the momentum space essentially. Now in the limit beta m goes to 0, only the sigma dot alpha dot p will appear essentially in the matrices. So the solution will become E chi 1 chi 2 in the momentum space E psi is equal to now where did I get this equation? Go back, go back, go back, go back, go back, go back. Remember alpha, this is your equation essentially, E psi is equal to alpha, this is nothing but your Dirac Hamiltonian. E psi is equal to alpha dot p plus beta times, this is your Dirac Hamiltonian. And we expanded it, wrote it down explicitly. This is the where we wrote it down. Okay, this is sigma dot p, this is nothing but on the diagonal entries, this is sigma dot p. If I take I del 0 is nothing but E psi and m becomes 0. So in the limit m goes to 0, this is the form it gets essentially. Okay, in the limit okay, in the limit momentum m goes to 0, essentially in the limit m goes to 0. Now you see this just becomes a much simpler equation essentially. this is just becomes a much simpler equation. You have E chi1 is equal to sigma dot p chi2, E chi2 is equal to sigma dot p chi1. Now add and subtract these equations. Okay, so this gives me a very interesting set of equations. Okay, so this I define chi r L is equal to 1 by 2 chi 1 plus minus chi 2. Okay, so this gives me two equations. E chi r is equal to sigma dot p chi r, E chi l is equal to minus sigma dot p chi l. These are two eigenvalue equations you have. Okay. These are very important relations. These are called the Weyl equations essentially. Okay. Okay, just let me repeat essentially. So you have so in the massless limit, the Dirac Hamiltonian and the momentum space just becomes E chi 1 chi 2 0 sigma dot p chi 1 plus chi 2, where chi 1 chi 2 are the Dirac spinors essentially. These are the Dirac spinors. So okay, you can consider them to be u v or whatever meaning. Okay, so now E chi 1 is equal to sigma dot p chi 2 and E chi 2 is equal to sigma dot p chi 1. Now if you add and subtract them, you have chi r, chi 1 plus chi 2. Okay, the left hand side is the same essentially. So you end up having 1 by 2 chi 1 plus chi 2 chi r essentially. So if I define this particular case essentially as chi rl is equal to chi 1 plus chi 2 1 by 2 and chi 1 minus chi 2 is equal to chi l. This picks up a minus sign, minus sigma dot p, and these are called the Weyl equations. These fermions are the massless fermions of Dirac equation. And these solutions are two component. Two component spinors. Called Weyl spinors. So the Weyl spinors, both of them are independent solutions essentially. Both of them are independent solutions. Okay, they form irreducible representation of the Lorentz group in the massless limit. They form irreducible representations of the Lorentz group. So what does this solutions mean essentially? So to begin with, I started with psi is equal to some Dirac spinor essentially. So psi, okay, which has two components. Let me assume that to be they are chi1 and chi2, and now I take the massless limit. They are the two component spinors. Chi1 and chi2 are two component spinors. I decompose the Dirac spinor, which is a 4 component spinor. Imagine this to be, one can imagine them to be u, v, or any of the known things essentially of the two component spinors. Okay, UV spinors, or UV spinors can also be written in terms of two component spinors, right, essentially. Okay, so now what I did was I added and subtracted them essentially, and then you ended up having these solutions which are E of chi r and E of chi l, one with a sigma dot p operator which is negative, and another which is eigenvalue of the sigma dot p operator which is positive. And these are called, chi l is called the left movers essentially, and the chi r of the are called the right movers. In fact, you have chi r is equal to sigma dot p by mod p chi r. Chi l is equal to sigma dot p minus mod p. And this particular operator, the eigenstates of which chi l and chi r are the solutions of, and this particular operator is nothing but the helicity operator. The helicity operator is the projection of the spin in the direction of the motion essentially, the projection of the spin in the direction of the momentum. Okay, so the helicity operator sometimes it is also called sigma, spin operator, helicity operator, okay, sometime, okay, sigma dot p by mod p. These are massless fermions. Remember, the energy is nothing but m0 is equal to 0. They are massless fermions, and in the limit of massless fermions, the fermions, wild fermions are nothing but your the eigenstates of the helicity operator. So what we introduced is something called the helicity operator. The helicity operator is the projection of the spin in the direction of the momentum. And what we saw right now is that the wild fermions are the eigenstates of the helicity operator. So this is important, the wild fermions are eigenstates of the helicity operator. Now what does this tell you that what does it tell you more essentially? So and now if there is a spin, okay, in the direction of the momentum, okay, so the spin is, and the projection of the spin in the direction of the momentum, okay, If it is parallel, projection of the spin is parallel, it is called right movers. Right helicity, that is the R which starts for, one is called the right, okay, right, and another is called the left. If it is in opposite direction, because you pick up a minus sign essentially, the projection of the spin is in the opposite direction to the direction of the momenta, these are called left movers, left helicity. In the last, in few lectures back, we have seen something called the chirality operator. The chirality operator becomes the helicity operator in the limit of massless fermions essentially. So, we have seen the chiral operator the projection operator, chiral projection operators. Okay. And the chiral operators, become, the chiral operators are defined for massive particles. Okay. The helicity operators also project the spin on the direction of the momentum. But are defined for massive particles. The difference between this, the chiral operators, the chiral projections are not independent. Chiral projections are not independent. Say for example, a right helicity object can never be, by in any frame of reference, a right mover can never become a left mover. Whereas there is always a frame of reference where a left helicity object can become a right helicity object. That is because you can never go to, because these are massless particles, they move with velocity of light. Okay. So, they move with velocity of light, okay. And so these are massless objects which move with velocity of light. So, there is no frame of reference in which a right mover can become a left mover. Where a left helicity object can become a right helicity object. Okay, there is no frame of reference, a left helicity object can become a right helicity object. So, that means that these are independent solutions, left chiral. Left helicity independent solutions. Chiral projections on the other hand are defined for massive particles. That means they all have masses. They will not travel with speed of light. They cannot travel with speed of light. That means there is always a frame of reference. You can always go to a frame of reference in which you travel with the speed of light. A left helicity object can become a right helicity object. There is so these are various these are the main difference between chirality and helicity operators essentially. Okay. In the massless limit, okay, in the massless limit, in the mass chiral objects, chiral states become helicity states. So, in the massless limit, that is the reason. Now, you may wonder why we need to define different operators for helicity, chirality and so on. So, because the reason why we need to define different operators is because one is for massive objects, one is for massless objects essentially, and the massless objects are independent solutions, whereas for the massive operators they are no independent solutions because they are always connected by the mass of the particle essentially. A mass of part of it. So, what is the relation between Weyl solutions and Dirac solutions? So, okay, I will write it as pictorially and then it becomes easier. So, Dirac solutions are particle up, particle down spin. So, these are particle solutions. So, this is what a Dirac spinor will contain. V up, V down, antiparticle solutions. So, what does a Weyl spinor contain? Remember, Weyl spinor is only two component. So, it contains left moving object, okay, which is particle up, antiparticle right, particle antiparticle. Together they form one chiral state, say let me call this as chi L. The other state would be with a helicity operator projection with so for opposite to momentum essentially. So, the momentum is down, P is down, essentially just a symbol, essentially P is down opposite to momentum. So, whereas This is towards momentum essentially. Okay, this is also towards momentum. So this forms the chiral object essentially, which contains one particle solution and one antiparticle solution, a left moving particle solution and a right moving antiparticle solution, and chiar contains a right moving particle solution and a left moving antiparticle solution. So this is the way you can classify the solutions of the Dirac and Weil spinors essentially. So this is one way of graphically remembering these solutions, and now of course you can explicitly write down the solutions what we had done earlier essentially p slash minus m and by this these things essentially. Okay. So but now to see the relation between these two operators, these two classes of solutions, is that the Dirac spinor contains all the 4 solutions, particle solutions and antiparticle solutions, both up and down, and spin up and spin down for the particle and antiparticle. Whereas the Weil spinor is very specific, it is a solution of the helicity operator. These are helicity operator solutions. So this contains chiral, which is particle left and antiparticle right, and chiar contains particle left and antiparticle solution. In this way you can see that the Dirac spinor is nothing but a combination of of 2 Weil spinors. Okay. So the Dirac spinor can be thought of as chiral 0 plus 0 chiar, okay, is a combination of 2 Weil spinors in the massless limit. Okay. And in the massive limit it just becomes a combination of 2 chiral fermions, okay, chiral solutions, which are nothing but chiral and chiar essentially. Okay, which are, instead of these solutions which are becoming helicity solutions, they end up being what do you call chiral operator solutions. Okay, good. So this is about Weil solutions. Remember, the Weil solutions are independent solutions essentially. They are definite states of the Lorentz operator, and we can always decompose the Dirac spinor into a Weil fermions, and vice versa, combine 2 Weil fermions in terms of a Dirac spinor. Okay. So this kind of so either one uses 4 component notation or 2 component notation, there is always this kind of flexibility we have, such that depending upon the problem, and we can either use helicity states or the chiral states, and express the Dirac spinor either in terms of 4 component spinors or 2 component spinors essentially. So remember this, the Dirac spinor has 4 independent solutions, and the Weil spinor has only 2 independent solutions, but a combination Dirac spinor can be written in terms of 2 Weil spinors. And in future we will see also another class of solutions for called the Marrone solution, which are called Marrone fermions, which are particles which are their own antiparticles. Okay. So I'll stop here, and we'll meet in the next class. Okay. Thank you very much.